All right. Hello everyone. Sorry. I recorded all the lecture, and what happened is I found out the software wasn't functioning, so it did not get recorded. But I have all the notes written, so therefore I'm going to go over the notes again. So therefore, you guys can have a better understanding of what this lab 2 is about. Okay. All right. First of all, lab 2 is based on one of the example questions in the lecture, and also it's a same as one of the questions I ask you during the exam. So it's very simple. If you have a cantilever beam like here, mounted in the at the end, and you have a piece of piezo mounted on the at the fixed end of the cantilever beam, when you push it down, you are going to have force right here, right? F force push it down. So therefore, it's going to cause deflection, and the PL is going to give voltage. Remember that, right? That's a question, I believe, number 2 in the exam. Okay, so this lab, we're trying to demonstrate that, and we're trying to let you see using this, we can do some testing of it. All right. So all this lab is about is I'll show you here. Let me undo these thing. Okay, so what we're going to do is we're going to have uh, cable on top and bottom of the piezoelectric, and connect that to oscilloscope. All right, oscilloscope is going to record the voltage as a function of time. Okay, now we're not going to apply any certain force. Okay, what we're going to do is we are going to give it some initial displacement in the vertical direction, and then let it go. Okay, so this beam will vibrate, will under vibration, right? Like here. So once it vibrates, it's going to generate lots of strain at the fixed end, right? So therefore, the piezo is supposed to give you some voltage as a function of time. Okay, so the objective of this lab is we're trying to use piezoelectric ceramic sensor to determine the first natural frequency of a cantilever beam. Okay, so first natural frequency means when the beam is mounted in the bottom and then give some initial displacement, you let it go, it's going to vibrate. That vibration frequency is first natural frequency. Okay, and we are going to compare the theoretical. Let me use a different color. The theoretical and experimental results. So I am going to spend the next 10 minutes or so to give you the theoretical background of it. How do we use mathematical equation to determine the frequency of it? But in the same time, using the piezo, we can experimentally determine the frequency of the beam, right? And then we compare these two. Okay, should be the results. Anyway, so the theory behind it is very easy. So this equation, omega n equal to alpha n squared square root ei divided by ml the force. This is how it's determined. All right. So this omega is angular velocity, which is a radius per second. Okay. So n is the number of mode. For us, it's the first mode for our experiment. So basically, like I mentioned, we give it some initial displacement on the cantilever beam, let it go. The beam is going to vibrate under the first natural frequency. Okay. All right. So n equal to 1 force. So the equation comes down to this. So n equal to 1. So omega 1 equal to alpha 1 squared times a square root ei divided by ml, the force. Okay. Now alpha 1 is a constant, which is equal to 1.875. Okay. I'll give you this constant. And the E, of course, is Young's modulus. The beam we're going to use is aluminum. So it's really close to 69 times 10 to the 9 Pascal. Okay, 69 gigapascal in other words, right? I, everybody knows I, right? You guys calculate this all the time. So it's 1 over 12 base times height the cubic. Okay, I is that. And also this M is the mass. Now this is a very special mass. It's cross-section mass. So in other words, it's equal to density times the cross-sectional area. It's not the volume mass. Okay, it's a volume averaged mass. So basically, it's equal to the density times the cross-sectional area, which is equal to h times b, height times base, right? So it's a, in other words, it's a length linearified density. So basically, what you have is this M over here equal to rho times B times H. Okay, so it'll give you a cross-section, unit cross-section mass. L, easy, length of the beam, right? You measure that from the free end all the way to the fixed end. Okay, all right. So that's what you need to measure. Now, once you have all these numbers, alpha 1, E, I, M, and L, this is something you can measure, right? The only thing is a B and H, which you need to measure. So we'll give you a caliper to measure the base and height, all right, of the beam. Now, once you have all these numbers, you can calculate this omega, right? And we know frequency and omega, frequency equal to omega divided by 2 pi, right? So therefore, once you calculate this omega 1 divided by 2 pi, that is your theoretical frequency, okay? So the final equation comes down to this. I'll highlight that in yellow. So this is your theoretical value that you can predict by measure all these dimensions of the beam, base, height, and the length, and also from all these parameters I gave you, right? Young's modulus, alpha, and the length. Of course, you measure that. Anyways, so this is our theory, and below is our experiment. So the beam, when it vibrates, it goes up and it goes down, right? Now when the beam bend, if you it goes up, it's something like this, right? So therefore the top is under compression, bottom is under tension. While if it bends downwards, it's something more like that. So the top is under tension, the bottom is under compression. So basically this piezoelectric material right here is undergoing tension and compression as a function of time when the beam vibrates, right? So therefore the voltage you can record from the piezoelectric, will look like something like this, okay? Now of course the beam, eventually the vibration is going to stop, right? Because it has a damping. So the voltage in real world, it's going to look like something like this. Initially high amplitude, then slower, and slower. Becomes almost zero later, right? So what you can do is you track all these data, and then we're going to give it to you, okay? So make sure you bring a jump drive, so we'll record data for you. So from experiment, the frequency is equal to this number over here. F1 prime stands for the experiment, okay? Equal to 1 over T2 minus T1. Okay? Now T2 and T1 is coming from here. If you pick a peak value over here and peak value over here, it's going to give you the voltage and the time, right? So you have V1 T1 and V2 T2. So from here to here, point here to point here, it's a one period, right? So therefore, from here to here, T2 minus T1 is how much time it takes to finish one period. Now, if you do 1 over that is your frequency. Okay, makes sense? Or you can do something like this. The red dots over here, red dots right here and right here. Okay, now this is 0, this is 0. Now from time T3 or T4 on these 2 points, this is also from 0 to 0. So this is also one period. So you can also calculate one frequency, right? So I encourage you to do multiple. Maybe you can do F1 prime 1, F1 prime 2 based on different points. Okay, maybe peak to peak or 0 to 0 or bottom to bottom. Okay, so therefore you have a more averaged, more accurate measurement of the frequency from the experiment. Now we have the F1 predicted by the theoretical equation, and we have F1 prime, which is measured by piezoelectric. Then you compare these two numbers. Okay, now it should give you less than 10% of error. Okay, now I tried it. It's like only less than 2% of error. So by all means, I think whatever you do, if you didn't make a very accurate measurement, the difference, the error between these two should be less than 10%. If it's higher than 10%, chances are that some calculation or some data processing you're doing is wrong. Okay? All right. And then for the lab, so today is Tuesday. We're going to do the lab on Thursday. That's all groups. Okay? So this is a very simple experiment. So therefore, I don't think it takes that much time. Each group will only take maybe 10 minutes or so. All right. So at April the 40th, which is Thursday, let's go to the Lockheed Martin lab, the same lab you guys did the first experiment. All right. Now the class time is 10:30 to 11:50. Right. Okay. So for group 1, you guys do that first from 10:30 to 10:50. I'll give you 20 minutes, but I think really 10 minutes is enough of time, okay? And then group 2, you come in from this time slot. Group 3, 11:10, and group 4, 11:30, okay? And make sure you bring a jump drive, so therefore we can transfer the data to you, so therefore you can start to process the data after the lab. Now, some of the students are telling me about they don't have enough time for the lab report because some of the students are having like 5 or 6 projects together during these like couple weeks, right? I understand this is the end of the semester, so everybody's busy. So what we need to do is I will give you more time, all right? So if you need more time, go ahead. So but by May the 7th, end of the day, 11:59 p.m., you have to send me the lab reports of 1 and 2 together, all right, to my email address right here. So you don't have to print that out. All you need to do is just send me the electronic version of it and copy all your group members if you can, right? So this is the last time I can give you to finish up your lab report, okay? For both lab report 1 and lab report 2, you can send me that then together, okay? And that's it. So just email to me for the lab report. That's all we need. We don't have final exam for this class, so once we submit the lab report, you'll be good to go, okay? And that's pretty much it. And if you have any questions, feel free to send me email. I'll try to answer that. And if not, I'll be back by Friday. So if you have any questions, feel free to drop by on Friday. If you can catch me, of course, and I'll answer your question, okay? Other than that, that's pretty much the end of the class. So if you have any questions, feel free to send me email, okay? All right, have a good lab session. I'll see you guys later, okay? Bye.